Hey everyone, welcome back to another round of calculus, and we continue the conversation about area and approximating the area under a curve. In our last session, we talked about using rectangles or Riemann sums to approximate the area. We've now spent 2 days kind of covering the idea with some different setups, whether it be from tables, whether it be from functions, and we've seen that rectangles do a pretty decent job. We know that left hand and right hand tend to produce over under approximations, or a midpoint approximation seems to be the best option yet. When it comes to the approximations, we're hopefully more comfortable with things like this, doing the 3 different ones I've described. In a perfect world, we would try to make all the rectangles the same width. We know that in questions that involve tables, sometimes we'll have to stray away from them being the same width just to make it fit if we don't have the equation. If we do have the equation for the function, we generally can make the rectangles the same width no matter what. We also talked about the calculator, using the calculator to find the exact area. We're still kind of working towards this when it comes to showing the work by hand, but it is nice to kind of see what the exact area would be, so that way you can compare your approximations with the exact value and you'll know for sure if they're over or under. And today we start the conversation about trapezoids. So the first thing would be just kind of a quick refresher on trapezoids back in geometry. So if you remember the area of a trapezoid, the area formula was 1/2 times the height times the quantity of base 1 plus base 2. Now in this case, I also like to say that 1/2 of the height could also be written as the height over 2. Since fractions multiply straight across, you can put height over 1, and you can say height over 2 times the sum of the 2 bases. In this case, the height is going to be the distance from base 1 to base 2. Base 1 and base 2, how you organize them doesn't necessarily matter. In this case, they're calling base 1 the top and base 2 the bottom. But since we're just going to add them, we know that the order of addition doesn't make a big difference. So as a quick example, if you had this guy, you had a height of 4 and then base of 7, 11, your calculation would be 1/2 times the height, which is 4. 1/2 of 4 is 2. Take the bases, add them together, down 7 plus 11, 18, multiply, and you get 36. So when it comes to approximations, we'll take this idea and we'll extend it. So the integral from a to b of a function dx is approximately delta x over 2. And if you're taking a look at these trapezoids, maybe the first thing you'll notice is they do a pretty darn good job of approximating the area under the curve. For example, if you're looking at this one, you can say that's just a slight underestimation, slight overestimation, slight overestimation. Maybe not the best when it comes to these two sections. If the graph has pretty extreme concavity, or really high points and low points, sometimes it's hard for the trapezoids to adjust, but for every one that's not so great, like let's say this one, maybe one of the worst ones, there are ones that are very, very close. In general, I would say that this is going to be better than the left hand, the right hand, the midpoint. I would put trapezoid up there, maybe with midpoint as some of the best options that we have. In terms of the picture itself, what is delta x? What are we going to have to take in consideration? Well, maybe look up here in this box and you'll notice that the first thing we have is delta x over 2. Now we know the height of a trapezoid is going to be the distance from base 1 to base 2. So if I look at the far left here, my first trapezoid, I have the 2 bases. You can call this base 1 and this base 2. You'll notice the notation kind of calls it like base 0 or base 0, and this is base 1. And in this case, the height's going to be the distance between them. So just like in the last 2 days, we talked about the width of the rectangles being delta x. In this case, delta x is going to behave as the height. In a perfect world, you'll notice that here the delta x's are all going to be the same. If you have the equation, again, same idea, you will be able to take that and pull it out as a GCF or a constant. So if you're looking at this delta x over 2, that is the same thing as the 1/2 times the height. And then notice here we start collecting some of the bases. Now, how many times am I going to need these bases? Well, you'd agree, just kind of looking at the picture to start, I already have base 0 and base 1 that I'm using one time. But then if I move on to my next trapezoid, maybe I'll do this in a dashed red line, you'd agree we have to use base 1 again, and then we're going to get base 2. If I continue on this with different colors, then I'm going to need base 2 again. I have it in purple. And then I'm going to have base 3. If I do the next one in orange, I got base 3 again. And then I got base 4. And what you'll quickly notice is that all of these ones here in the middle we're using 2 times. So if I go back to blue, right? And then if I move on to the next one, I am using that one again. But then when I get to the last one, notice that when we get to the last base, which is here in purple, I'm only using it one time. So if you're looking at the notation up here, you'll notice the first base has a coefficient of 1. Everything in the middle has a coefficient of 2. And then the last one also has a coefficient of 1. And the reason why this is if you think about the trapezoids, we're really just using this base on the far left one time and this base on the far right one time. But then aren't we using all these subsequent bases in the middle 2 times? So to speed things up, you'll see that they're actually multiplying them by 2. So going down the line, in a perfect world, before we start jumping in, we can pull out the 1/2 times the height as a constant or as a GCF. So we know that this part is going to stay consistent for all the calculations that we're doing. Of course, base 1 plus base 2 is going to change based on which trapezoid we're talking about. And now we know for a fact that the far left and the far right bases are only going to be used one time, where everything else in the middle is going to be used 2 times. So let's get to it. Let's see an example. So in this case, example 1, approximate the following integral using 4 trapezoids. So the first thing I would take into consideration is what is the height of these trapezoids going to be. So to find the height of the trapezoids, I would take delta x and then divide it by n, just like what we did for the Riemann sums. In this case, if you look at the integral itself, it's starting at 0 and going to 2. So for change in x, it's going to cover 2 units. We're going to use 4 trapezoids and let n be the number of trapezoids, just like n was the number of rectangles in the Riemanns. 2 over 4 is going to be a half. So in this case, I know the height of each trapezoid that I want is going to be a half. So then thinking about the formula, I know that the formula for area of a trapezoid is, again, 1/2 times the height times the sum of the 2 bases. Just going down the line, I'm going to start with 1/2 and the height, which in this case is also 1/2. And those are going to be the constants for all my calculations. In this case, I'm going to start building the bases. I know that we're starting this at 0, and I know that at 0, we're only going to use that base one time. So then that base is going to be f of 0. You'd agree just by looking at this piece, the bases are determined by the height of the function, or the y value at the x values that we're interested in. So then what about the next one? Well, because we're no longer on the far left side of the trapezoids, I know the next piece I'm going to use 2 times. And then what is the x value that we're interested in is going to be a half. And if I continue down the line by adding a half, 2 times f of 1, 2 times f of 3/2, and of course now we've reached the end, this would be f of 2. Notice the slight difference between this and the Riemann sums is that here, if you look at the bases that we have, there are actually 5 different bases. And if you're thinking, well, we have 4 trapezoids, why 5 bases? Is because we're going to need a base for the top and the bottom of that trapezoid. So where if this was Riemann sums, we would expect to just see 4 values here. It makes sense that we see 5 values for trapezoids. So if I multiply here on the outside, I have a half times a half, which is a quarter. Just going down the line, I'm not sure how much of this we're going to have to plug in a calculator anyway, but let's just practice simplifying some. So f of 0, I know the function is e to the x squared. If I plug in 0, e to the 0 is going to be 1, plus 2 times, if I take a half and dump it into the function, this will be e to a quarter, plus 2 times e to the first, plus 2 times e to the 9/4, since fractions multiply straight across, plus e to the 4th. If you take this into the calculator for this entire piece inside of here, again, you can pause the video if you want to double check it. I got 82.578. And then if I times 1/4 times 82.578, I got a final answer of 20.645. Now, if you want to take out the calculator and try to find what the exact area for this would be, again, you could do that. The cool part about using the integral feature on the calculator is that you could check it for any function. So if you want to pause the video and check, you're more than welcome to. For our purposes, I would say that's going to be a pretty darn good approximation. So I'll continue on into example 2. In example 2, they give us the integral from 0 to 8, and they ask us to do the trapezoidal rule with 4 subintervals. In this case, 4 subintervals, you can think about that as like 4 trapezoids. So subintervals just means how you're breaking up the entire region. I'm breaking it up into 4 pieces, into 4 trapezoids. No calculator. And then we'll draw a little bit of a picture so you can kind of see what's happening behind the scenes. So first things first, if I was going to attack this one, I would want to know what is the height of my trapezoids going to be. So then, how about right here, we can say, let's find delta x over n. I can see the integral starting at 0 and going to 8, which means x is changing by 8. We want there to be 4 rectangles, so I think 8 divided by 4, 2. I want all of them to have height of 2. So if I'm continuing the idea with good notation, the integral from 0 to 8 of the function with respect to x can be approximated. Again, I know I've said it a few times, but I'll just kind of repeat. 1/2 height times the sum of the bases is the generic form for area of a trapezoid. I've got 1/2, and then the height of 2, which is going to be pulled out as the constant here. The 1/2 and 2 are going to actually end up canceling each other out, which I'll show in a moment. But how about just going down the line? I know that I'm starting the integral at 0, which means 0 is going to be the first base of the trapezoid. I'm only using it one time. And then the next one, from 0, we're going to go to 2. But since it's not the far left to the far right, I'm going to use it 2 times. So then I'm just going down the line. 2 times f of 6. And then at the end, I reach f of 8. And a friendly reminder, I'm only using f of 8 one single time. Since 1/2 and 2 multiply straight across to 1, we can cancel them off. And then just going down the line, if I plug in, maybe I'll put 1 on the outside just to emphasize it. If I take 0 and dump it into the function, again, the function is just x squared. I'm going to get 0 plus 2 times 2 squared, which is 2 times 4, which is 8, plus 2 times 4 squared, which is 2 times 16, 32. Going down the line, 6 squared, 36 times 2, 72. And last but not least, just 8 squared, which is 64. If you take a moment to add all these up, you'll get something like 176. Is the answer an overestimate or an underestimate? Let's go ahead and draw a picture. So we know that the first trapezoid we're doing was from 0 to 2. So then 0 kind of has like a starting point, and then to 2. To draw a trapezoid, just extend a line from one to the other. And hopefully to agree, just by even looking at the first trapezoid, I can see that it appears to be an over approximation. So then what about if I go from 2 to 4? All right, I probably will attempt to draw this better. So there we go. And for this one, you can see that there appears to be a slight over approximation as well. So then if I'm just going down the line, and then just looking at it, maybe in purple, you could say this part here would be the over approximation there. And then it appears we have a slight over approximation here as well. So if I was going to write it out, I would say that there's going to be an over approximation. And then the reason why, the concavity. So if I'm looking at the function itself, the concavity will be the reason. The concavity of the function causes the over approximation. So different concavity for different functions will cause different things, but in this case, it is going to be an over approximation. All right, so that is example 2. Feel free to pause the video if you want to revisit it. How about for this one? This was very similar to a question that was on the assignment from yesterday. The trapezoidal rule and left and right Riemann sums were used to estimate this integral, where f is the function whose graph is shown below. The same number of subintervals were used to produce each approximation, and the estimates were provided here. So I'm going to do some drawing on this function itself. Maybe I'll start with a left endpoint. So if I was to do a left endpoint for a Riemann, I know that Riemann is rectangles. So it would look like this. Hopefully you would agree that for a left-handed approximation, it appears to be an over approximation. If I do a right-handed Riemann, so then drawing the rectangle back this way, hopefully you'd agree this guy is going to be an under approximation. So this is right-handed. And then for a trapezoid, if maybe I draw it off here to the side, trapezoid approximation appears to be very close. Probably a slight over approximation, but in this case, definitely better than the other two. So looking at the numbers that I have here, just going in sequential order, right? 0.7811 is the smallest, which would mean that it would have to be the under approximation. If it's the under approximation, it would have to be right-handed. If I skip over to 0.09543, that's the largest. that would have to be the over approximation, so then that would be the left-handed one. 0.8675 is in the middle, is the best of both worlds, and then that would have to be the trapezoidal approximation. So in this case, it's not too bad to determine which one produces which one. Just consider the fact that the concavity of the function will determine whether left hand or right hand is over or under. In this case, the trapezoid would always have to be the one in the middle, since it's kind of the best of both worlds. So example number 3 complete, and that's the rationale, just drawing in the picture and getting a sense of what the concavity is telling you. So how about example 4? This is similar to the extra bonus example that I did in yesterday's video. I think it's actually maybe even the same table that we have. And it says, given the values for f of x on the table above, approximate the area under the graph from -5 to 5 using a trapezoidal approximation. All right, so then we know, again, area formula for trapezoid, 1/2 height times the sum of the bases. So let's just dive into notation. I've got an integral from -5 to 5 of a function. I'm going to try to approximate it with a trapezoid. But in this case, if I look at x, I'll notice that the x values are not changing in a constant manner. From -5 to -3 is going up by 2. From 3 to 0 is going by 3. From 0 to 1 is going to be going up by 1. And from 1 to 5 is going up by 4. So I see there's my 4 trapezoids. There's the 4 subintervals that I'm kind of interested in. But then think about this. What could I pull out of each and every calculation? Well, the 1/2 for sure will be part of the conversation for each trapezoid that I find. But then notice that the height, delta x, is not something that is constant. So for that reason, I can't pull out the height in this one, where in the other examples I did. For the same reason as yesterday, I don't have the equation. In a perfect world, I would try to get the trapezoids to be the same height, but in this case, I can't. So I'm going to pull out the 1/2, and the 1/2 here that I'm pulling out is not the height again. It's the 1/2 that comes from the formula for area of a trapezoid. I'm going to open up a big set here, so a big set of brackets, and then I'll just go down the line talking about the trapezoids. So then here for my first trapezoid, I see that it has a height of 2. Again, it's this guy here. And then if I look at the sum of the bases are going to be 10 plus 7. So on the far left here, 10 and then 7. And then plus, that would be my first trapezoid, so I move on to the next one. The next trapezoid has a height of 3, and the sum of the bases, 7 plus 5. If I then scoot over to the next trapezoid, it's got a height of 1, and then the sum of the bases, 5 plus 8, plus the last trapezoid, which has a height of 4, and the sum of the bases, 8 plus 11. So just going down the line, this one's not too bad either. I think we can crunch the numbers here. So then 2 times 17, 34, plus 3 times 12, which is 36, plus 1 times 13, which is 13, plus 4 times 19, which is 76. If I add these down the line, it's not too bad either. It kind of works out friendly. I think we'll get to 159. If I multiply straight across, this will be 159 over 2, which is just 79.5. So in this case, we do get a final approximation of 79.5. If you're wondering in your head, where is the 2 times all the bases that are being used, you can actually see it here. Now you're not building with the formula, but if you look at the far left values that we would have for the y, we have 10 and 11. And if you look at our calculation, notice how we only use 10 and 11 one time. If we look at all of the other bases, you would agree 7 is being used 2 times, 5 is being used 2 times, and 8 is being used 2 times. So even though it is a little bit different than using it with an equation because we're kind of building it from the table, we can see the same kind of thing that is arising. Now, there was no constant height that we could pull out, but you would agree that once we got past the 1/2 as the coefficient we can pull out of everything, the rest of it was kind of standard from there. And that's not bad. Again, table questions, I'm hoping eventually for you become something that you don't mind and something that you would take on willingly, since everything's in front of you and usually the calculations are not too terrible. All right, so example 4 in the books. So what about the next one? For the next one, we have example 5. Estimate the area under the graph in the figure below by using a trapezoidal rule with 8 subintervals. So just looking at it, I can see that we're going to be starting this guy at 2 and going to 10. So maybe I'll calculate delta x over n. In this case, from 2 to 10 covers x values, or 8x values. We want there to be 8 subintervals. We want 8 trapezoids. 8 over 8 is going to be 1. So if I dive right into the conversation, I'll say the integral of this function from 2 to 10 can be approximated using trapezoids. We can pull out the 1/2. as the part of the formula that's consistent to all. We can also say that in this case, all of the trapezoids are going to have a height of 1. So I can pull that out as well. And going down the line, since we're starting at 2, we're going to need f of 2 one time. We'll need 2 times f of 3, 2 times f of 4. And you can definitely speed this part up if you want with some, like a dot, 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 to kind of show that the pattern continues. I'm going to write it all out because I'm in charge of the explaining. But if you want, you could speed it up. So everything is going to be used 2 times except for the first and the last. So notice here, once I get to 10, I'm not multiplying it by 2. So for this one, I would imagine if we were all doing it separately, we would all get different answers. So I'm just going to eyeball it, and you'll see if you agree with me or not. So starting out front, 1/2 times 1, 1/2 as the coefficient. If I go to f of 2, there's probably no dispute about f of 2, 0, plus 2 times f of 3. If I go to f of 3, that's about halfway. So in my book, I'm going to call this 1.5. Plus 2 times the next one, which is really close to 2, I'm going to call that 1.9, plus 2 times f of 5, which in this case is just a little bit more than 2, I'm going to call that 2.2, plus 2 times f of 6, I'm going to call that 3, plus 2 times f of 7, I'm going to call that 3.8. Again, there would be some flexibility if you were doing it yourself, but we're getting close. So then about f of 8, that one's kind of friendly. I think that comes back exactly at 4, plus 2 times f of 9, which I would say is exactly 3, and then f of 10, which is back to the x-axis, which would be 0. So then if you take the time to actually take all these things in the bracket and add up all the things in that quantity, I got something like 38.8, and if I take half of 38.8, I'm going to get something like 19.4. So in this case, using trapezoids, I approximated the area to be 19.4 units. Now, if they gave me something like meters or centimeters, I would say things like centimeters square, meters square. Here it's just generic units, so you could say units squared if you want. All right, so that'll be example 5. Now, how about example 6? For these examples in the notes, maybe I failed to mention you probably need to draw, so if you want to pause the video so you can draw them in. They don't have to be super crazy sketches, but I will give you the idea. So how about this last one? Example 6, the widths in meters of a kidney-shaped swimming pool were measured at 2-meter intervals, as indicated in the figure below. Use a trapezoidal rule to estimate the area of the pool. Now, even though this one may seem very different than example 5, it turns out is really exactly the same question. But the reason it makes it more tricky is that here we're kind of given an x and y axis, where here we kind of have to like self-impose an x and y axis. So here's my favorite way to do it. So maybe I'll use purple. So on the far left side, I'll call this kind of like the y-axis and call this guy the x-axis. So we have these. And then imagine that I took these points and I pushed them down. So like I pushed down on this kidney shape so that it was touching the x-axis. Notice for the 6.2 it already is touching. But then if I push this guy down, I want it to be touching the x-axis entirely. If I do this by pushing it down, then I think it will actually produce a shape that looks something just like this. So going down the line, to not make the picture too busy, I'll erase some of these lines that I've drawn in here. But imagine that we've taken this and we've pushed it down to the x-axis so that we have values. What would that mean about this first value here? If I pushed it down to the x-axis, that would be 0. Going down the line, the rest of these heights would stay the same. And then for that last point, if I took it and pushed it down to the x-axis, it would be 0 as well. So in this case, delta x over n, it doesn't really tell us what the change in x is since we don't know, but they do give us that we're going to be doing 2-meter intervals. So in this case, I would imagine that means the 2 is going to be the height of each trapezoid. So if I just go purely by what we have here, you could just say this is the integral of the function dx, since we don't technically know the x values. But you can say it can be approximated. We know it's going to be trapezoid, so 1/2 comes from the formula times 2, which is going to be the height. In a very satisfying way, those are going to cancel out in a second. And then how about just going down the line? For 0 here, we're only going to use it once. Then, of course, we're going to use 6.2 2 times. We're going to use 7.2 2 times. We're going to use 6.8 2 times. 5.6 2 times. 5 2 times. And then 4.8 2 times. And then at the end, we have one single 0. So then the 1/2 and the 2 cancel each other out. If you take the time and run this guy through the calculator, what I ended up getting was 80.8. So this will be 80.8. And then since they gave us that the units were in meters, we could say this is in meters squared, since it is an area. All right. So in this case, I think that completes the examples. Even though example 6 looks drastically different, it is actually very, very similar to the idea that we just did in example 5. So if you continue on in the packet that I gave you last week, you'll see that there is an AP practice set. So look for the question that says, a rocket has positive velocity v of t after being launched upward from initial height of 0. And then it just goes into some questions. Notice how I present some tables to you. It does ask you to explain using correct units what things mean, and then look out for subintervals as telling you how many trapezoids you are using. So I'll provide an answer key on Canvas for this so that you can check it as you go. Friendly reminder that if you have a velocity time graph and you integrate it, just remember that the area under a velocity time graph is the total distance traveled. So in this case, I think that will help. All right, guys, so please give it a chance and check the answer key as you go. I'm hoping that the little conversation here about trapezoids made sense, and feel free to reach out if you have any questions. All right, have a great rest of your day. Good luck with the assignment. Peace.